What actually is escape velocity and the trajectory? Ever wondered just how fast you need to go to break free from Earth's gravity? Today I'm going to explain the concept of escape velocity in the simplest terms possible. First off, escape velocity is the speed an object needs to escape a planet's gravitational pull without any further propulsion. Think of it like this. You're tossing a ball up into the air. If you throw it lightly, it comes back down. Throw it a bit harder, it goes higher but still returns. But if you could throw it at escape velocity, it would keep going and never come back. So what's this magic speed for Earth? About 11.2 kilometers per second, or roughly 25,000 miles per hour. That's incredibly fast, like traveling from New York to Los Angeles in about 5 minutes. But remember, while the term escape velocity sounds like it's all about speed, it's actually about the energy required to overcome Earth's gravity. Now, what if we're talking about a different planet or a moon? Escape velocity changes because it depends on two things: the mass of the celestial body and the distance from its center. Larger and more massive bodies like Jupiter have higher escape velocities, while smaller moons and asteroids have much lower ones. For instance, the moon's escape velocity is only about 2.4 kilometers per second. That's why it's much easier to launch from the moon than from the Earth. But this speed is still mind-bogglingly fast compared to our everyday experiences. Now, here's an interesting tidbit. Objects in orbit around Earth, like satellites, are traveling fast, but not fast enough to escape. They maintain an elliptical or circular path because their speed is always less than the escape velocity at their current distance from Earth's center. Essentially, they're in a constant state of freefall, but moving forward fast enough that they keep missing Earth. But if an object is on a hyperbolic trajectory, meaning it's moving fast enough to escape, it'll always be traveling faster than the escape velocity at any given distance. In contrast, if an object is on a parabolic trajectory, it will be traveling at exactly the escape velocity. It's balancing just right between being captured by gravity and escaping it altogether. Let's not forget about the practical side of this. Space missions use these calculations to determine if a spacecraft will remain in orbit or venture out into the solar system. They also use gravity assist to gain extra speed without using additional fuel, borrowing kinetic energy from planets. And while rockets don't have to hit escape velocity all at once, they achieve it through continuous thrust. This way, they can gradually build up the energy needed to break free from Earth's gravitational grip. Now that we've grasped the basics of escape velocity, let's dive a bit deeper into the fascinating topic of escape orbits and trajectories. Imagine an object that has attained exactly the escape velocity, but instead of heading straight away from the planet, it's moving at an angle. What happens next? Such an object follows a curved path known as an escape trajectory. Unlike closed orbits, this trajectory doesn't loop back on itself. Instead, it forms an open shape, specifically a parabola, with its focus at the planet's center of mass. Why is this significant? Well, assuming gravity is the only force at play, the object's speed at any point along this parabolic path will equal the escape velocity at that distance from the planet. This is due to the conservation of energy. Its total energy remains zero, meaning it's always moving at escape velocity. Now, for an actual escape, the object's trajectory must avoid intersecting with the planet or its atmosphere. This path, when moving away from the source, is called an escape orbit, also known as a C3 =0 orbit. Here's where it gets even more interesting. C3, or the characteristic energy, equals gm divided by 2a. In this equation, a represents the semi-major axis, and for parabolic trajectories, a is infinite. If an object in a circular orbit, or at the closest point of an elliptical orbit, accelerates to reach escape velocity, the point of acceleration becomes the periapsis of its escape trajectory. This means the object will eventually travel at a 90-degree angle from its direction at the point of acceleration. But what if the object accelerates beyond escape velocity? In that case, the trajectory shifts to a hyperbolic path, and the angle of eventual travel becomes smaller, aligning with one of the asymptotes of this new trajectory. Timing the acceleration is crucial if the goal is to escape in a specific direction. These details might seem complex, but they're vital for planning space missions and ensuring that spacecraft achieve their intended paths. Understanding these principles allows scientists and engineers to precisely calculate trajectories, avoiding potential collisions and optimizing fuel usage. So, the next time you hear about a spacecraft embarking on a journey beyond Earth, remember the intricate dance of velocities, angles, and trajectories that make such missions possible. Stay curious and keep reaching for the stars.